Yeah, welcome to the virtual meet and mingle of the American Ceramic Society Energy Materials and Systems Division. It's the first event of this kind, of this new division, and I like to introduce this division to you. My name is Armin Felter from Leibniz University of Hanover in Germany. And this division has started this year as a new division of the American Ceramic Society, and it focuses on stimulating the growth and activities of the society in the arts and science pertaining to ceramic and glass materials for energy-related applications. We, this division, represent the society in matters pertaining to the science and engineering of ceramic and glass materials and related technology as they apply to the harvesting, conversion, storage, transportation, and utilization of energy. So broad topics related to energy, that's what we are interested in and what we want to support. The leadership of this division changes on a regular schedule. Due to the pandemic situation, the officers take over their offices for the next year. So that are me, Armin Felter from Hanover in Germany. The vice chair is Kyle Brinkman from Clemson in USA. The secretary of the division is Krista Carlson from the University of Utah, USA. And the program committee chair is Eva Hammer from the University of Ottawa in Canada. Eva is also the liaison of this division to the board of directors of the society. There is a student advisor delegate who relates the division to the President's Council. That is Michael Tuis from the Colorado School of Mines. There is also Fellows Nomination Committee, which is headed by Yute Kato from Oak Ridge. So quite some people are involved. And in the background, to show you some faces behind the event today that are these four. The division offers quite some volunteer opportunities and also student awards. The student awards are travel stipends or outstanding student researcher awards for scientific meetings, can be poster awards or whatever is the activity of the division there. And the nominations for these things are usually put on the society website, can be found there, and there are descriptions of all these topics. And the volunteer opportunities can be posted judges at conferences or so on. And there came up a new volunteer opportunity with online communities. This is a kind of chat room which has been established for each of the division of the American Ceramic Society and offers a community to have an open dialogue among the topics of the division, in our case, energy-related topics. And volunteer opportunities with these online communities are moderators or super members. The role of this is to keep these dialogues vibrant, give a response, activate people to give response, and so on, that there is really vibrant community in this online community. But the volunteer opportunities go far beyond this. And for graduate researchers involving PhD students, the Global Graduate Researcher Network might be of interest. So if you are not yet member of the American Ceramic Society, but are interested in the topics and may consider to become a member to get involved, it's at only $30 per year, but even better, our division currently sponsors memberships. This program runs until end of this year. So if you are interested, please contact one of us, Kyle, Krista, Eva, or me. The emails are on the flyer of this virtual meet and mingle, or in the web page of the society. So we sponsor your membership up to 4 years, and the first 2 years would be free, and for the second and fourth year, each year it's 50% off, so $15 per year for the third and fourth year only. So if it's of interest, come and reach out to us. And please enjoy the virtual Meet and Mingle today, which is moderated by Eva, involves science, young investigator activities, breakout rooms, and two speakers, Daniele Benetti and Claus Daniel, with energy-related topics, which are hopefully of interest for all of us. Please enjoy. Thank you.
Thank you very much, Armin, for the general introduction. So I also would like to mention that, first of all, welcome to this really first experimental and virtual get-together. I believe we are all missing real in-person interactions, and virtual meetings can only be a kind of a cover to try to get over this, waiting to meet each other in person again. But I hope this will at least provide an opportunity to get a bit in touch. And as Armin mentioned already, the plan is that we will have our two great speakers today, which is my honor to introduce to you shortly. And then afterwards, if you have time to stay, we can also make some breakout rooms in to get together and to chat. Of course, whenever you have questions, there will be time for this. So after each of the presentations, either you can type them in the chat, or after each of the presentations, we can have a live session in question and answers. I'm sure our speakers will be happy to answer to you. So having said this, with no further ado, I would like to invite Claus to maybe share his screen so that we can get started. And while he is doing so, I would like to give a brief introduction about him and his bio. So maybe a small fun fact aside, at least like for US and Canadian dimensions, we are both coming from the same town, more or less, where we grew up as children. And we went to the same university in Germany, Saarland University, where we both studied materials engineering, just like 1 year apart. And so Dr. Daniel, he obtained his master's degree, or at the time it was a diploma, in material science at the Saarland University with summa cum laude, and in collaboration with the Max Planck Institute for Metal Research. In addition to this, he also spent some time in France, where the Saarland University started at the time, or just like it got more and more popular, a really strong collaboration with the university in France, with actually the an engineering schools in material science in Nancy, in Lorraine, in France. So he got a double diploma from both the German and the French university. And this might also be something like a shout out to students that we hopefully have here in the audience to advertise a bit or to advocate for opportunities. If you get an opportunity to study abroad, I think this is always a great idea. So after graduation, Claus moved then to the US, to the Oak Ridge National Lab, where he now is actually the program manager coordinating the ONRL's cutting portfolio with the Advanced Research Project Agency in terms of energy and hydrogen, fuel, solar cell, and wind portfolio. He also holds a professorship at the University of Tennessee in Knoxville, and is the board president of and a co-founder of the 10 Smart, as I learned, a public-private partnership with the goal of advancing intelligent mobility in Tennessee and also elsewhere. He has published a large number of papers, over 200. He holds a number of patents and patents that are still pending. He has, among others, also received the National Academy of Engineering Gilbert Lectureship Award and recognitions. So, furthermore, he is also a Carverley alumni of the National Academy of Science. So today he will speak to us about reducing society's carbon intensity and creating a circular carbon economy to solve humans' biggest centennial challenge. So we are really looking forward for your presentation. And please, Klaus, it's really great to have you here. Thank you for accepting the invitation, and the screen is yours.
Thank you very much, Eva. Very much appreciated. I take, since you got the title of my talk right, I assume you can see my screen. Is that right? Excellent. Okay. Well, I want to thank all of you. I want to thank Armin and Eva and all of the organizers for today's first Meet and Mingle here for inviting me. It's very exciting. I'm happy to be here and honored to have been asked sort of to be the inaugural speaker, if you will, for this new division and do the Meet and Mingle here. I also want to welcome everybody who is online here. I think we're close to 40 people, so that's exciting. And I assume we're probably spanning from, you know, anywhere from Europe all the way to the West Coast or so of the United States. So welcome, everybody. With that, without further ado, let me see if I can actually move this forward. Yeah, I want to start off here a little bit. Some people might still remember this logo. This actually goes back to 2015 when the international community got together in Paris for the COP21. And at that time, they agreed to essentially find new ways to reduce our carbon intensity. They signed an agreement to reduce each of our carbon emissions to essentially maintain a level of less than 1.5 degrees Celsius increase in global temperature. And that required us to make some really drastic steps. Who you see was doing is he was making an appeal to the developed nations to create carbon space for developing nations to grow into. It just told me here that my internet speed is unstable. I hope you can still hear me here. Hope that will not get a bigger problem as we're moving forward. I find that appeal very interesting because it actually means that we would not just need to get carbon neutral, but we would actually have to create negative emission technologies. But nevertheless, for today, I want to just look back into what was the United States contribution at the time to this climate summit. At that time, our energy secretary was Ernest Moniz, and this is one of his big statements here. Essentially, was saying clean energy innovation is the solution to climate change. And at the Department of Energy, we hold true to that. The Department of Energy programs in the United States is really looking at how can we help our clean energy innovations to advance dramatically and increase in speed of innovation. At Oak Ridge National Laboratory, we just recently created a new directorate, which is our Energy Science and Technology Directorate, and it is the directorate which is in charge of ONL's agenda for clean energy systems. I'm sitting in that directorate, and in that regard, I'm leading our ARPA-E and our hydrogen, our fuel cell, wind and solar programs to really contribute to that agenda heavily. In 2015, ONL's contribution to the climate conference was this nice car here. This is a 3D printed vehicle, and it has a full electric powertrain. It also has some advanced technology in it where we're looking at utilizing recycled carbon fiber composites, rare earth-free electric motors, other types of clean powertrain technologies, and then integration of these electric vehicles with other technologies like building technologies, using clean carbon-free electricity and things like that. You see here actually at the time he was our vice president, and he's now president-elect Joe Biden. He has a very strong climate plan, and we hope that under his leadership we will be able to continue to contribute to this agenda heavily. Here you see that car actually on the exhibition floor in Paris in 2015 at the climate conference. This statement here is taken straight out of the Biden administration climate plan. His idea is to ensure the US achieves 100% clean energy economy and reaches net zero emissions no later than 2050. And that is subscribing to that goal of what happened in 2015. I'll bring a graph up later why we need to reach net zero emissions by 2050 in order to truly have the impact we need on the climate. With that, let's go back here a little bit and see what else is going on and what are some of our motivators. Eva was talking a little bit about the National Academy of Engineering. I've been working very closely with a number of their program committees to help shape the agenda. And in that regard, the National Academy has defined 14 grand challenges for engineering in the 21st century. One of those challenges is what they call develop carbon sequestration methods. In that regard, they're actually looking at can we engineer our way to capture and store excess carbon dioxide? I would challenge them on this goal and say we actually need to go further. Not just store the captured carbon dioxide, but really this is a call for action to make carbon dioxide a valuable precursor for fuels and products. Can we really bring some value to it, use it as a precursor for industry across the board? And if we achieve that, I think we can have a true impact on net zero carbon emissions across the world by 2050. So let's have a look. Why carbon and why is carbon important here? So this is a graph here. I'm going to run it as a video and I hope it will work well and come across. It's looking at our carbon intensity, essentially what you see on top here, hold on a sec. Can you see my cursor?
No.
Hold on,
but maybe
can you see it now? It's very small for some reason. Well, okay. Well, but on top that the axis is CO2 emissions in tons per person, per capita. And on the bottom, you see the income per person in purchasing power adjusted GDP, right? And it runs from 1800 to 2018. And let me run it here. Oh, now you can see my cursor probably. Let's see if I can make this run. Oh, there we go. Now it runs. I hope you can see it run. So you see two colored bubbles starting to get bigger and run up on this. One is for in the European Union for Germany, which is the biggest economy there. That's the orange. And the yellow is for the United States. And what you see is they have essentially one direction going up. As we accumulate wealth, we also increase our carbon intensity. In the last 20 years or so, you saw it come down a little bit on both of those nations. So we're making some progress, but we're far from where we need to be. If we look at some of the progress we have made, you can see that while our GDP here in the United States grew about 33%, our carbon emissions reduced by about, just shy of 20% between 2000 and 2015. However, most of these are essentially coming just from the electricity sector. And I will show that a little bit more here in just a second. When I take the electricity and the transportation sector, I look at both of those. This is specific for the United States. In 1990, we had roughly about 1,470 million metric tons of CO2 emissions in transportation and about 1,830 million metric tons in CO2 emissions in electricity. 1 decade later, it looks like this. I call that the lost decade. This was really, really bad, where we were becoming very, very dirty in both areas and continue to really increase our emissions. If we look at yet 1 decade later, pretty much stable. Nothing has happened on there. In 2010, we sort of had some awakening and said, we got to do something. And when we look at that, what happened 10 years later, or about 7 years later, we made substantial advances in our electricity sector, but nearly nothing in transportation. And if we compare it back to 1990, essentially we have just a small dip, about 3.7% reduction there, but we had a 22% increase over 1990 in transportation. And that is unacceptable. So we really need to tackle that. Transportation is really our hardest to decarbonize sector in our economy. And I think that is a big problem all around the world. So in that regard, this is that graph I was referring to earlier, which is sort of the motivation for the Paris Climate Agreement. And it shows essentially that if we want to keep the United States, if we want to keep the world at less or maximum 1.5 degrees Celsius increase of temperature, then we really need to hit zero carbon emissions by 2050. If we're anywhere above that, we're going up quite dramatically. So how do we do that? Well, let's have a look. This is an eye chart. I don't expect you to look at all the details of it, but one key component I want to point your attention to is if we look at electricity here and we look at transportation here, then we can sort of compare a little bit of what's happening there, right? In 2018, the vast majority of our resources for electricity for our carbon emissions came essentially from natural gas and coal, and from our transportation came all from petroleum. If we compare that to our energy, we see why we could make improvements in our electricity sector in terms of carbon, because we have a lot of carbon-free resources being available for our electricity production: solar, nuclear, hydro, wind, and geothermal, right? While in transportation, we have really nothing coming.
Seeing this figure for so long.
Sorry, go ahead. Somebody was trying to say something.
Go ahead, Klaus.
Okay, no worries. So, and that is the big reason why we had not been able to really decarbonize transportation at all. It's still heavily dependent on petroleum and just a sliver of electricity coming in. These are all of our electric vehicles here, the 0.03. So what do we look at? Let's go back to electricity for a second and have a look at what we're doing in that space. Low carbon electricity is actually becoming very affordable. If you look across the board on how much we pay, we're looking here essentially, what you see here is solar, wind, nuclear, coal, and gas. And when you look there, is that essentially wind by now is the cheapest electricity source, followed by solar, and then followed by nuclear. Coal and gas are actually dramatically more expensive by now. That is a good sign. That helps us really going forward and continue to decarbonize our electricity grid. When we want to do that, what keeps us from doing that, other than the cost, is this is again an eye chart, but I will walk you through some of those. This shows in the United States the several regions of electricity production. And when you look at that, it looks essentially at some interregional considerations here. It looks at a forecasted supply. In each of these boxes, you see a forecasted supply of carbon-free electricity, and it shows an estimated demand of carbon-free electricity. And when you compare that, in most regions, it's okay. We just have a few regions where, like for example here in the West, where the estimated demand might outstrip the supply. But if you look at some other regions where you have surplus, you could actually balance the whole grid across the board. However, that balancing is a challenging aspect on there because we haven't had that investment infrastructure in the past. So at Oak Ridge, what we're doing is we're working with a number of other laboratories together and are trying to design how would the grid of the future look like? What do we need? And there are two key technologies we need. One is high voltage DC stations, which are strategically located across the country, and then high voltage direct conducting transmission lines to really connect those regions. And that way you're able to move wind and solar resources from where they happen to be to where your electricity demand is. This can be compared very much in Europe, for example, to that big north-south trass in Germany to bring wind power from the North Sea all the way down to Southern Europe or Southern Germany in that regard. Mobility and transportation is slightly different, and the challenge is slightly bigger. And that's going back to where our resources are coming from. If I look at that again, the energy consumption, this is just a more simple version of that graph you've seen before. Our energy consumption essentially is pretty much a third in each one of these three sectors: transportation, buildings, and industry. But since transportation is 96% plus petroleum and very little non-petroleum here, that's the reason why transportation is responsible for more than 50% of the non-electricity carbon emissions. And that is a big problem. So what else can we do? Well, let's have a look how we can bring renewable electricity into transportation in a more effective way than just electric vehicles. I stole this slide in parts from Shell. Every big energy company in the world, international energy company, they have some version of this future view. When you look, you take renewable electricity, you can put it straight into electric vehicles at a very high efficiency level and run those. But electric vehicles have some issues that sometimes they don't satisfy your range, sometimes they're too heavy, sometimes you don't have enough electricity storage on board. And so you got to find other ways to do with it. So if you now look, you can transform your electrons with electrolysis and water into hydrogen. Well, you can get some services here. At about 70%, you can turn it into hydrogen, but 55%, you can use it in fuel cell electric vehicles. You can go further up the chain. You can create chemicals, methanol, ammonia, formic acid, things like that. You can actually turn it all the way into hydrocarbon. You can make synthetic gasoline or synthetic diesel, which is a drop-in fuel to regular vehicles. And what you then do when you run those vehicles, you emit the carbon you have just recently captured. So now all of a sudden you can be carbon neutral even with a combustion engine. So when you look at that, how do you look through a whole portfolio of technologies? If you compare average mileage per day by application or trip and weight of the application, you see essentially passenger cars down here. You come up to heavier and heavier vehicles, all the way to rail, aviation, and shipping. And when you look at these colors, the dark blue is opportunities for battery electric vehicles. The light blue is opportunities for fuel cell electric vehicles. And the lightest shade of blue is the opportunity where you cannot satisfy that with either batteries or fuel cells. You need a liquid energy carrier, and that could be a CO2 neutral fuel synthesized from water, carbon dioxide, and renewable electricity. The tricky thing is, how much energy do we really need? And with that, I wanted to show you a little bit what the daunting task looked like. In the United States, we provide roughly about just shy of 15 exajoule per year of electricity energy, right, through our electricity grid. In order to produce that, well, sorry, I apologize. I got to first take this. In transportation, we're consuming about 30 exajoule. So twice the amount of electricity energy dispensed through our electricity grid is being used in transportation. That's rather daunting. Now it becomes even more difficult when you look how much primary energy we actually use to generate this electricity. The primary energy consumed to produce 15 exajoule of electricity is 40 exajoule. When you compare that now, in order to then deliver your 30 exajoule of electricity for your propulsion of vehicles, you would actually need something of the order of about 80 exajoule of primary energy. That is really daunting, right? That is essentially a dramatic shift here. And how do we solve that? Well, let's have a look. We obviously need to reduce the total amount of energy we need in that regard. And when we look at our current transportation fleet, and we assume about 100% of that is petroleum, we're pretty much close by. If we take the medium and heavy duty sector, which is the hardest to decarbonize, what can we achieve? We actually believe that we can reduce about 20% of the energy consumption by introducing new lightweighting materials and increase our freight operational efficiency. We believe we can reduce another 60% by hybridizing some of these powertrains, even if we don't make them all electric, and then increase their advanced engine and emission controls, so make those engines more efficient. So now we're down to 20% of that initial need. So when we use that as a full fuel substitution, we believe we're at a level where we can actually tackle the task. Now, how do we do that? That's our opportunity. We have an opportunity to completely restructure our electricity grid and introduce liquid fuels and other energy storage modes to make this work. Let's have a look at our current electricity grid. We currently have a peak capacity in our electricity grid of roughly about 1 gigawatt. We have an average consumption in the United States of about 475 gigawatts. So that makes actually a balance. Oh, sorry, we also have 25 gigawatts of storage currently available. So that makes a balance of, roughly a little more than a half a gigawatt, if you will. That balance actually is what we have our load following generation capacity. That's our gas powered power plants and things like that. They constantly ramp up and down. It actually makes the electricity grid a rather a poor operation in that, because we only have about a 44% asset utilization at the moment. Any plant manager who would run a production plant at 44% capacity would probably be fired by their company. The electricity grid is exactly that. So let's see, what could we do? Let's assume we take on the daunting task of more than doubling our electricity production. Let's say we bring it up by 1.3 gigawatts to 2.5 gigawatts of maximum generation. That's a daunting task. However, let's see what else we can do. We take our prior average down, right? So we consume still in our buildings and everything we do, roughly about 475 gigawatts. We then dump about 1.3 gigawatts right into electrolysis and chemical processing for liquid fuels and electricity for charging electric vehicles. This takes care of the entire energy demand by our transportation on-road fleet. We increase our energy storage capacity by just merely a little bit. This is only about 6 times as much as this, right? And then we introduce intelligent loads. Those are appliances that communicate with the grid and can react to the grid. Water heaters that can slightly increase or decrease the water temperature when the grid either needs electrons or has surplus electrons. Fridges that can slightly adjust their temperature without spoiling food. Washing machines that can slightly delay the cycle by only about 5 minutes or so if you need capacity, things like that. When we do that, we only have a balance of 150 gigawatts left. Now, compare that to the total, and now you have, with all of your responsive, flexible loads and energy resources, a grid that has a 94% asset utilization. You have 1.8 terawatts of energy storage resources in your grid, and you can actually make a profit off of this at the same time as you completely decarbonize your grid and your transportation sector. So with that, there is some issues to solve along the way. One is, what are our energy, carbon, and hydrogen resources we're looking at? What is our fuel processing and fuel distribution infrastructure looking at that? And what are our high efficiency technologies to reduce our total energy demand to work through? And with that, we have to ask a lot of questions, and we have to solve a lot of those engineering challenges in the decades to come, hopefully just one or two, to really solve these problems so we can work on implementation and really achieve our goal of 2050. One of the things to be considered, and I promise you I will not go too far into the science of fuels here, but I want to point out a little bit, we're looking at some trade-offs here. When we really synthesize fuels, we don't have to live with what we get out of the ground. We can actually revisit what do we really want to achieve. When you look at the synthesis of fuels, essentially the higher your molecular weight becomes, the more expensive the fuel is to produce. On the other side, the higher your molecular weight becomes, the more expensive it is to consume. So in that regard, you look at a trade-off. Where do I have high expense on the production side? Where do I have high expense on the consumption side? And where is my sweet spot? Somewhere in the middle here is my molecular weight sweet spot, where I get an optimized energy output and CapEx and energy intensity input. With that, I want to just point out, this is my second to last slide, to show that there's a large number of companies already on board looking at opportunities to become carbon neutral in the oil and gas industry, in the automotive industry, and then in business and finance. And all of those have some goal either before 2050 or around 2050 to truly decarbonize their businesses and their products. With that, I want to thank you, and I'm open for any questions either now or maybe after the second speaker of today. Thank you so much.
Wonderful. Thank you so much, Klaus. A big virtual applause. And yes, we have time for questions. Either feel free to speak up or put your question in the chat if you have any. I don't see any for the moment, but maybe so I would like to...
Either the talk was so boring that everybody slept in and can't have a question, or it was so clear that all questions are answered.
Absolutely. But no, I'm actually happy. So your before last slide, there it was written, Formula One will go carbon zero by 2030. This is in 10 years, right? If I remember correctly.
That's right. Yep.
Yes. So, I mean, I'm not a Formula One fan, neither do I have any clue how it works, but just seeing these cars, to me, it sounds like they are really like needing a lot of gas. And it seems to be like quite a challenge to bring this to zero carbon. How comes that they can aim to be like zero carbon in 2030 and then like other big companies are not able to reach this earlier? Or in a more general way, where do you see are the big hurdles and limitations that we need to overcome, either in terms of scientific developments or in terms of public mindset to reach our goals in time?
Yeah, thank you, Eva, for that question. So I think actually Formula One is a perfect example on how we can sort of overcome these apparent conflicts where we think, well, that's never going to happen, right? So if you look, so Formula One actually, the FIA, they currently have a Formula E series as well. Formula E is all electric. It's like an open wheel car, all electric. What they do, the electricity they use to charge those vehicles is essentially based on a synthetic fuel, which is actually even edible. I forgot what exactly the compound is, but I have been at a Formula E race and I was offered a glass of that. and I could drink it, and that's what they run. They run it actually through through their electricity generators to produce the electricity to charge their batteries. So in Formula One, they're going to continue with combustion engines. Their power units these days have a large battery in them to provide additional power, but the main power source is still going to be a combustion engine, even in 2030. The fuel they're going to use for that combustion will be a synthetically produced fuel. And in that regard, you can look at it, CO2 capture, electrolysis of water, creating essentially using CO2, using green hydrogen, and then chemically processing it to a hydrocarbon. And that way you become carbon neutral.
And is this then also, I mean, at the end, you have to take into account every single step, like also the energy that is needed for the chemical reaction. It's a bit like you can go for solar cells to make it green energy, but all the energy that is needed to produce the solar cell, it's like to become really carbon neutral.
Yeah, life cycle analysis is really important for these technologies. The other one is you have to account for carbon. So there is sort of a concept around, every carbon atom counts. So I can make a reaction like that 100% carbon efficient, even though it's not 100% energy efficient, right? So I got to make sure if I have any release of carbon, I capture that carbon and I turn it back into a useful product. That costs me energy. As long as that energy is a carbon-free energy, I will never get 100% energy efficient, but I will be able to account for every carbon, right?
Yes, Kyle, go ahead.
Yes, this is Kyle from Clemson. Great talk, Claus. And I had a question on natural gas. I know you oversee Oak Ridge's RPE and EERE programs. The last 5 years or so, there was a number of RPE programs on natural gas recovery, utilization. What's the current thinking in DOE on natural gas and the path forward?
So I think our thinking of natural gas might actually change in the next few years a little bit. I think there is a lot of renewed attention on methane leakage associated with natural gas production, and methane is I think it's 8 times more potent than CO2 as a greenhouse gas. So that is really, really important. We currently have about a 4% leakage rate. So that makes it really, really dramatic. There are some programs at ARPA-E looking at methane leakage and opportunities to reduce that. There's a new program called Remedy, which looks at utilizing that properly and also make products out of it. The vast majority of hydrogen these days actually is not green hydrogen. It's what's called either a blue or gray hydrogen. I think 96% of our hydrogen is gray hydrogen, which means it's produced from coal or natural gas without any carbon capture technology. Blue hydrogen is hydrogen produced from natural gas with carbon capture technology. So I think in short term, the DOE will continue to look for advances in carbon capture and carbon utilization technologies. In the long term, I believe we need to truly solve the problem to get completely away from fossil resources and use only renewable resources to essentially solve our problems on there. I do not believe in carbon storage. I think that problem is way too hard and too big. And if anybody looks at geological storage for carbon dioxide, then I would just ask them to look up the 1986 disaster at Laos Lake in Cameroon, which we're not quite sure yet why it happened there, but there was a lot of carbon stored in the water deep in the lake, and something initiated a lake turnover, and which resulted in a massive carbon release at that lake. and over 1,700 people died of carbon dioxide poisoning. And so if we look at that, if we start doing geographical carbon storage, I would be very, very worried about it. And that's why I believe we need to properly fix carbon either in mineralization or we need to utilize it in products.
So,
Hi, Klaus. Yeah, a nice presentation. I really loved your data visualization and analytics. So in your view, what would be the most promising biofuels in terms of cost competitiveness, like ethanol, diesel, and etc.? Some companies are investing heavily in this. For instance, ExxonMobil is investing a lot of money in producing biofuels from algae. They think that would be promising. So any promising biofuels that you think?
I truly believe that biofuels is actually going to be a key component of becoming carbon neutral. I think we should not just focus on synthetic fuel only, but I think we need to do the biomass involvement very responsibly, right? So I think there continues to be a debate about when does biomass compete with the food chain? There continues to be some issues with what are we going to do with nitrogen and phosphor runoff and associated algae problems and dead zones in coastal regions. I think those will all need to be answered, right? And when we're looking, our current technology enables, so at the moment, with our current fertilizer technology and our current technology around agriculture, the Earth is estimated to have a food production capacity for 10 billion people. We're currently 8. And I forgot when we are crossing the 10 million mark, but before we cross the 10 billion, but before we cross the 10 billion people mark on Earth, we need to solve our nitrogen problem. We need to increase our nitrogen efficiency in terms of fertilization and reduce our nitrogen runoff. And only when we solve all of those challenges, we can have a good coexistence of biomass for energy production and food production, I believe. Does that answer your question? It probably created more questions than answers. It's a big problem, right?
Yeah, thanks, Klaus. Yeah, it does. Yeah, I think food versus fuel is an important debate that's been going on in the industry. Yeah, so one of the technologies that is cellulosic biomass. So instead of actual food, they're trying to use cellulosic biomass to generate a biofuels. Yeah, but that was a very nice point. Yeah, thanks, Klaus.
Yeah, I agree with that effort very much. The tricky question is always, what is your secondary effect, right? Because if you grow that type of biomass, have you or have you not actually displaced another food production source, right? That kind of thing. So what would have happened on that area if you hadn't used it for this?
okay, I'm seeing some more people unmuted. If you have a question, just please speak up. We can have another one. If that's not the case, then I think we should thank Klaus again. And great discussion, wonderful talk. And thank you, Klaus. So, but if your time allows, please stay with us, and maybe there will be some more discussion afterwards.
Absolutely, I will hang around. Thank you very much. And you all can find my contact information. If anybody would like to follow up later, I'll be more than happy to engage. Thank you. Thanks for having me today.
Thanks, Klaus.